Dr. D-Flo.
Hey guys, it's Dr. D-Flo, and in today's video, we're going to be building a CNC plasma cutter. If you're not familiar with plasma cutting, then let me give you a quick rundown. This technology uses a hot plasma stream to slice through conductive metals. Plasma is generated through an electrical arc that heats surrounding gas to a temperature so high that electrons are ripped away from their nuclei. This ionized gas is known as plasma. Within the plasma torch, compressed air forces plasma through a nozzle, forming the plasma stream. The three main requirements for plasma cutting are a torch, a power supply, and compressed air from either a gas cylinder or an air compressor. Manually operating a plasma cutter is relatively easy. Press a button and cut. However, getting clean cuts is much harder. The speed at which the torch moves over the material and the distance the nozzle is from the material impacts the cut quality. As I am a beginner, it's easy to see that my technique leaves a lot to be desired. Having the positioning, speed, and height of the torch controlled by a computer and linear actuators will not only allow for better cut quality, but will also allow for designs to be cut automatically. There are a lot of pre-built CNC plasma cutters on the market, some of which are priced very competitively. However, for maintenance reasons, and because I like to build things, I'm going to go the DIY approach. As I was planning out this project, Mark Carew, the founder of OpenBuilds, reached out to chat about my How to Build a 3D Printer video, which, as you may have seen, used linear actuators from OpenBuilds. I had mentioned that I wanted to build a plasma cutter, and to my surprise, he said that he and his team were currently designing a DIY kit and asked if I wanted to help test a beta version. I quickly jumped on that opportunity because, to be honest, I was most likely going to use the OpenBuilds platform anyways. However, I do have to disclose that while I wasn't paid to make this video, I did receive the kit for free. Let's walk through what came in this comprehensive kit. On the mechanical side, we have linear rails, of course. We also have plates and wheels to make the carriages, lead screw and anti-backlash nut blocks to move the carriages, and a lot of hardware to attach everything together. Electrical components include NEMA 23 stepper motors, limit switches, and wires that are already cut to size, which is awesome. The electrical components will be connected to the Blackbox motion controller. I've never used OpenBuilds motion controller, but I think it's going to simplify the electrical setup of this machine. We will start by assembling the linear motion system, which is based off of OpenBuilds' pre-existing lead machine. Fortunately, the OpenBuilds team has already released multiple videos on how to assemble the mechanical and electrical portion of that machine. And my How to Build a 3D Printer video broadly covers how to build with V-Rail. To avoid redundancy, this video will speed through the assembly of the linear actuators and focus on the components unique to the plasma cutter, such as the floating head. Well, let's get to it. Here we have a 3D rendering of what the lead plasma machine will look like after assembly. It's a gantry style machine where the table will remain stationary and the plasma cutter will move in all three dimensions. Just so we're on the same page, this is the X direction, this is the Y direction, and this is the Z direction. We'll start by following the instructions for the lead machine by putting together the carriages and rails, and then move on to the plasma cutter specific elements, such as the floating head and the table. We made quick work of putting the carriages together. I hope you can appreciate how user-friendly the OpenBuild system is. So far, I've only used an Allen key and a wrench. Next, we're going to put the carriages on the rails and install the lead screws. So I finished the linear actuators for the Z and Y axes, but let's pause and talk about the lead screws used in this plasma cutter because it's a bit uncommon. Most commercial and DIY plasma cutters use rack and pinion transmissions to move their carriages along their respective axes. Rack and pinion configurations are most desirable for machines that cover long distances and for messy work environments like those created during plasma cutting. I've seen some cool designs on the OpenBuilds forum where people have used a rack and pinion setup with the V-wheel system, but this is generally much more expensive than using a lead screw. I'm also not really concerned about grit and slag getting into the lead screws because the lead plasma is configured in such a way that the C-beams face away from the work area, protecting the lead screws. I'm going to finish the X actuator, then I'm going to tie all the axes together, and then we'll catch up again. This is looking like a plasma cutter now. As I mentioned in the beginning of the video, when I was performing manual cuts, the distance between the nozzle and the top of the material is very important. The irregular shape of the plasma stream can cause excessive beveling of the cut edges if the torch is too high or too low. For this reason, most plasma cutters have a sliding torch mount that allows the height of the torch to be adjusted. With cheaper plasma cutters, you have to set this distance manually at the start of each job. However, a floating head allows this process to be automated. Here's how it works. At the start of a cut, the Z-axis will lower the torch and eventually the nozzle will come in contact with the material. Without a floating head, the torch would just snap if the Z-axis continued to lower after contact. However, with the floating head, the torch can oppose this downward movement by moving upwards. A switch located at a known distance from the top of the floating head will be triggered once it moves up high enough. For our example, let's say the switch is triggered after the floating head moves up 5 millimeters. Once the switch is triggered, the microcontroller coordinating all the movement will know that if the Z-axis moved up 6 millimeters, the torch will be 1 millimeter away from the material to be cut. The floating head is particularly useful when you're cutting out multiple designs from a single sheet. Before each cut, the plasma cutter can recheck the distance between the material and the torch, which is important because most material is not perfectly flat and can become warped as you plasma cut it. Here's how I built the floating head for the lead plasma. V-wheels were attached directly to the Z-axis and allow a short piece of 20 by 40 V-rail to ride between them. A rubber stopper on the side of the V-rail prevents the rail from slipping too far down and losing contact with the wheels. I attached the plasma torch to the 20 by 40 millimeter rail with a 3D printed holder. I'm hoping that this holder won't deform from the heat created during plasma cutting. I'll keep an eye on that during the initial test cuts. For the floating head to operate properly, it has to return back to its original position after moving upwards. I noticed that the friction of the V-wheels was too high for gravity to overcome, so I added a spring to add a little extra downforce, which appears to do the trick. With the plasma cutter taking shape, I wanted to build the stand so that I could free up my bench. I did it off camera because I was just screwing together aluminum extrusion. However, I did attach casters to the stand with a 3D printed part so that the plasma cutter is mobile. I should mention that all the files for the 3D printed parts, including the caster adapters and the torch holder, are available on my website alongside supplemental information that you may find useful if you're new to plasma cutting. Not gonna lie, it's a little tall because of those 4-inch casters, but it moves really smoothly. Next, I'm gonna run wires to the stepper motors and set up the limit switches as well as the floating head switch. To start off, I'm gonna mount the X, Y, and Z limit switches. These are optional for plasma cutting because having a machine home is not super useful. Unlike in milling, where you need to return to the same location on the workpiece after a tool change, you only have one torch for plasma cutting. Also, the wires that connect the limit switches to the black box can act as antennas for electrical noise. I'm installing limit switches for now because it'll be nice to have the torch front and center after the homing routine, but I may ditch them later if I'm having problems with noise. Now I'm going to wire this plasma cutter like I would any CNC machine. I'm running 3 conductor wire for the switches and 4 conductor wire for the stepper motors through drag chains to keep them out of the way as the gantry moves around. Unlike CNC routers and 3D printers, plasma cutters can generate electrical noise that can damage the stepper drivers and microcontroller that are used to control the machine. This noise is transmitted from the torch to the microcontroller through the stepper motor and limit switch wires. Proper shielding of the cables and grounding of the machine can mitigate this noise, but typically you have to bury a grounding rod close to the machine to lead this high frequency noise away from the sensitive electronics. However, sticking an 8-foot copper rod into my garage floor is not something I'm willing to do. Now, not all plasma cutters emit this high frequency noise. Plasma cutters that use a technology known as blowback start do not need a high AC voltage to start the plasma stream. This technology is definitely preferable for CNC, but is significantly more expensive. My noisy little plasma cutter only costs $200, so for those on a budget, this could be a great option if I can get it to work. I have anecdotal evidence from a friend that careful spacing of the plasma cutter's power supply and wires from the CNC frame, along with the use of ferrites, can cut down on some of the electrical noise. I'm using OpenBuilds Blackbox to coordinate the movement of the stepper motors and respond to the triggering of the end stops and floating head switch. Within the Blackbox is an Atmega 328P microcontroller running Gerbil, 4 4-amp stepper drivers, and a relay for switching on the plasma cutter. This is my first time using the black box, but after reading the documentation, this seems like it'll be quick to set up, which is great for those who are trying to avoid more complicated control systems like those that use Linux CNC. I connected my PC to the Blackbox via USB. I'm using the OpenBuilds control program to send commands to the Blackbox from my computer. Because the plasma cutter is based off the lead machine, we can select that configuration, which will send all the appropriate parameters to the Blackbox. However, one setting that I need to check is the direction of the stepper motors. The direction the motors move will depend on how I wired each one to their respective stepper drivers. I will jog each axis to make sure that what I'm seeing on the screen corresponds to real life. For the x-axis, the positive direction should be this way. However, when I click move in the positive direction, we get the opposite of what we would expect. No problem, we can just invert the direction signal for the x-axis motor without having to switch any wiring within the control software. And now everything works as expected. Let's move the y-axis. Away from me is the positive direction. I got lucky with the wiring here, no change needed. Moving up is the positive direction for the z-axis. However, we're already maxed out on our upward movement, so I'm going to move it downwards, hopefully. This also worked without having to change the direction signal. So after making that change for the x-axis, all the axes are behaving as they should. Next, I need to see if the homing cycle works. Each axis should bump into its respective limit switch, back off a couple millimeters, and then bump that switch again. This extra cycle is known as debouncing, and it yields a slightly more consistent home location. The homing cycle is flawless. Finally, let's test the floating head switch. I placed a piece of material here, and we're going to go ahead and probe that surface. And there it is. With the floating head, the Z-axis was able to sense the presence of the material. Next, we need to talk about the hazards of plasma cutting. This process produces a smoke of metallic particles that can be absorbed into the body through the lungs. Regular exposure to this smoke can lead to significant health problems, including cancer. There are two ways you can minimize your exposure to these toxic fumes. The first is to relocate all the smoke and dust outside. This is accomplished through a downdraft table, which uses a blower to suck down and push the fumes through ducting, which leads them outside after passing through a set of filters. The second option is to trap the fumes with a water table. In this setup, the material that is being cut sits on slats that are within a pan of water. The compressed air from the plasma torch will push the dust and smoke into the water after piercing the material, which keeps those metallic particles out of your shop air. The water table is not only cheaper than a downdraft table, but it is usually more efficient at collecting the smoke. I purchased this 20 gauge stainless steel drip pan off of Amazon for the water table. The pan is undersized in the Y direction, about 8.5 inches shorter than I would have wanted it to be, but all the quotes I received from local sheet metal fabricators were around $1,000 for a custom pan. These high prices for one-off parts is why I'm trying to expand the metalworking capabilities of my garage. I started off with the mill and will soon have the plasma cutter completed. I will be acquiring and building more metal-focused machines in the future, so hit that subscribe button to be notified of these future projects. Let's talk a little bit more about this pan. The pan is 2.5 inches tall, which doesn't leave much clearance for the torch. To add a little more room, I'm going to flip these 20 by 40 cross beams to be horizontal, which will allow the water table to be recessed down into the frame. I don't expect to be cutting any material thicker than 3/8 of an inch, and I will have plenty of room to do that. That small adjustment gave the torch an extra 20 millimeters of clearance, or about 3/4 of an inch. I also like this change because now the pan is seated within the frame, so it won't slide around if I decide to move the plasma cutter. We can't take our material and place it on the bottom of the pan because then the plasma cutter would cut through both the material and the pan. We need to suspend the material on sacrificial slats. For the slats, I ordered 2.5 inch wide, 1/8 inch thick mild steel flat bar. The original plan was to have the slats close to the same height as the water pan so that it would be easy for me to load and unload material and also load sheets that are larger than the Y dimension of the pan. But now I'm starting to question this plan because of water level. Generally, the closer the water is to the material, the less smoke you will have. But if the water is too close to the top of the pan, the water will splash out, which would not be ideal with the Blackbox and power supply being so close to the pan. I think the plan now is to keep the water level 1/2 inch to an inch below the top of the pan. It may make sense in the future to use a 2-inch slat and have the material sit inside the pan so that it's closer to the water level for better smoke control. The slats fit really tightly within the pan, so I went ahead and drilled a small hole in the bottom of all the slats so that water can pass through. I will place a slat every 2 inches, and as a temporary way to hold the slats in place, I'm using small clips that I 3D printed. One of my first projects will be to cut a more permanent solution for holding these slats in place. excited to start cutting, but I came across a small issue. When I went to attach the pencil torch to the air and power line, I noticed that the threading on this male fitting did not match the threading on this PT31 line, which is the standard for these cheap Cut 50 plasma cutters. Because of current events, it looks like it will take a couple of months for me to get a replacement pencil torch due to it being an imported product. Given this delivery delay, I tried to retap the threads to the correct size, but I ended up breaking the plastic housing of the torch. It's a new plan. I'm going to attach the handheld torch to the floating head. This won't look as good, but there won't be any loss of functionality. 3D printing a holder for the handheld torch proved to be more difficult than the pencil torch, because the handle has to face away from the floating head so that the nozzle is perpendicular to the work area. Now from this orientation, there really isn't an obvious way to grab onto the torch head. I recently purchased some roller guides, which are basically training wheels for plasma cutting, that help you maintain the nozzle a constant distance above the work. The metal collar that the wheel's attached to turned out to be a great way to grab a hold of the head of the torch with my 3D printed holder. This assembly attaches to the floating head similar to the previous holder. With the high frequency start of this plasma cutter, I cannot run the air and power hose through the drag chain. It'll be in too close of contact with the low voltage stepper and limit switch wires. As an aside, it's always recommended to run wires connecting different circuits perpendicular to one another, as parallel lines are more likely to exchange noise. For the moment, I'll just let the hose flop around, and I will devise a more permanent solution when I know that I can get the plasma cutter to work even with the anticipated noise problems. I did take one measure to reduce noise though. As I had alluded to earlier, I installed ferrite chokes onto the wires that went into the Blackbox, as well as a USB cable that connects the Blackbox to the computer. I'm not going to delve into the theory of how ferrites work and why they should cut down the high frequency noise from the plasma cutter, but I will have some helpful links on my website. The last thing I need to do before taking some test cuts is to give the Blackbox control over starting and stopping the plasma stream. When you're manually plasma cutting, pressing the button is what completes the circuit, triggering the power supply to start the arc. We can replace the button with the relay found within the Blackbox. For demonstration purposes, I connected my multimeter, which is in continuity mode, to the screw terminals for the relay. This is a normally open relay, so when it doesn't receive power, the circuit is open, so the multimeter doesn't beep. However, when I send the M3G code to the Blackbox, the relay will receive power, which will close this circuit, resulting in continuity between the two leads of the multimeter, and it'll beep. With Gerbil, you can't just send M3, you have to include some kind of spindle speed or laser power. Even though with the plasma cutter it's either on or off, just for nomenclature reasons, we have to include S1000. Obviously, with the multimeter sound, we know that the relay is active and it has closed and connected those two terminals. The M5 command will stop power going to the relay. We need a long 2-conductor wire to connect the relay to the button input on the power supply. The Blackbox uses screw terminals, so we don't need to make any adjustments on this end, but the power supply requires an aviation connector to interface with that button input. So we'll add an aviation connector on this end. Okay, so I know it's only been a couple of seconds for you, but I've spent a better part of a week trying to get the noise from the plasma cutter to not interfere with the electronics. As soon as the torch generates a high frequency spark, the Atmega 328P inside of the Blackbox resets, which automatically switches the relay off so the torch shuts down. This occurred even with the ferrite chokes. I started to unplug wires so that there'd be less pass for this high frequency noise to lead back to the Blackbox. As I mentioned before, the limit switches are not strictly necessary, so I unplugged all 3 of those, although this did little to help. At this point, I was running out of ways to troubleshoot this problem, because to be honest, my knowledge of EMI is limited. What I do know is that it's important to keep the high voltage plasma circuit as small and short as possible, and to keep the positive and negative leads close together. Both of these measures will reduce radiated noise. I zip-tied the plasma and work clamp leads together, leaving a little extra slack in the torch line so that the machine could still move around. This alone didn't help. However, I had a small breakthrough when I started to think about the positive leg of the plasma cutting circuit. electrons jumped from the negative torch to the workpiece because they were trying to return the power supply to the positive clamp. The workpiece is resting on steel slats, which are in a stainless steel pan that is sitting on top of an aluminum frame. This CNC machine is made entirely out of conductive material. So in my head, this entire frame is the positive lead for the plasma cutter. To keep the high voltage circuit as small and short as possible, I insulated the workpiece from the frame through some blocks of wood. In this setup, neither the clamp nor the workpiece are touching the frame. And to my surprise, I was actually able to make some cuts without any errors from the microcontroller. Let me quickly walk you through this G-code that I used to cut that straight line. I'm using the floating head switch to probe the height of the material by the G38 command. I repeated this probing cycle twice, with the second time being at a lower speed for greater accuracy. To get the spark to jump from the plasma cutter to the work material, the nozzle has to be in close proximity to the material. Once the plasma stream starts, the plasma torch can be backed away from the material to a height that I'm referring to as the cut height. At this height, the plasma torch moves in the X direction, vaporizing any material in its path. I was able to expand this code so that the plasma cutter could cut out a square. Unfortunately, insulating the workpiece from the frame didn't completely solve the noise problem. Every other time the torch fired up, the microcontroller threw an error. This is simply not a robust solution to this problem. It also makes the water table less effective as the work material has to be resting on an insulator. I'm so motivated to get this Cut 50 to work for this CNC table because not only is it cheap, but the consumables are affordable. However, my time is also money and more drastic measures need to be taken to prevent electrical noise. If you are an electrical guru, please let me know in the comments below if you have any suggestions of what could be done without having to properly ground this machine through a grounding rod. It's time to move on to plan B. I'm excited to put this table through its paces, but I need a less noisy plasma cutter. Enter the Cutmaster 40 by Thermodynamics. This plasma cutter employs a technology known as blowback start, which uses a DC arc instead of a high frequency arc to ionize the gas and start the plasma stream. Electrical noise should be an afterthought with this plasma cutter. With these sleek plasma cutters, the circuitry for the torch is contained within one cable. This is unlike the Cut 50 where the torch trigger had a separate connection. I'm going to have to splice into the trigger wire inside of the power supply. In the manual, there's a pinout for the torch connection, so it's easy to identify which wires belong to the trigger. To splice into those wires, I'm going to use these T-tap wire connectors. If you've never seen these before, then you're in for a treat. The wire that you want to splice into sits in this metal V, and when you squeeze the connector closed, a small section of the wire insulation is stripped away, allowing the connector to make an electrical connection with the wire. Then a spade connector with a wire crimped to it is inserted into the other end. This is a very simple and clean way to splice into a wire. I use these tap connectors for both the trigger wires. I then checked with my multimeter just to make sure everything was in working order. The Cutmaster 40 uses an SL60 hand torch, so once again I'm going to 3D print a holder for it. Tightening an M5 bolt squeezes the side of the holder around the torch head. I was careful not to tighten the holder too much because I want the torch to pop out if I ever crash the Z-axis into the workpiece. This torch and its leads are of much higher quality than the Cut 50's torch and as a result are much heavier. I was a little concerned that the 3D printed holder wouldn't be able to support the weight of the torch and the leads, especially as the leads are dragged along. So I threw together this rail which will suspend the torch cable above the holder. I added this little carriage thinking it would move back and forth with the X motion of the plasma cutter, but in practice it remains relatively stationary. This addition still does its job by taking the weight of the plasma cutter lead off the 3D printed holder and making sure the lead doesn't get tangled when the plasma cutter moves around. There's plenty of slack. I attached the work clamp Next, I need to hook everything up to the power supply, including the compressed air line. Okay, we're ready for the first cut. We're going to keep it simple by cutting another straight line. Okay, that was best case scenario. It worked on the first try. You may have noticed that at the start of the cut, the nozzle didn't have to be as close to the material as the Cut 50's torch. This is because the SL60 torch has a pilot arc which ionizes the air, allowing a plasma stream to be started even when the material is far away. When the nozzle is brought close to the material, the pilot arc turns into the primary arc. As a side note, the pilot arc can cut through rust and paint, which can save a lot of time because surface prep can be skipped. Maybe you're wondering how far the nozzle should be from the surface during a cut. In the manual, it recommends 3 to 9 millimeters. This is specific to the type of nozzle that is being used. In this case, I'm using a standoff nozzle, which shouldn't be dragged during the cut. Because of the floating head, the Z-axis will have to move slightly farther up to get the nozzle between this range. I was shooting for about 5 millimeters of spacing. To achieve this, I had to move the Z-axis up 6 millimeters to account for the floating head. Now let's cut a design that lets us check the alignment of the machine. I'm going to use OpenBuilds free CAM software. That's right, you don't need a subscription to Fusion 360 or any other fancy CAM software to start cutting on the lead plasma. However, on a future design, I will show you how to use Fusion. But for beginners and those on a budget, the OpenBuilds CAM software is great. In the settings menu, I will select the Blackbox for the controller and OpenBuilds Lead 1010 for the machine, which is what this plasma cutter is based off. In the future, I assume that OpenBuilds will create a plasma cutter profile, but it's really not that hard to make the required changes. Let's delete the spindle and add a laser for the tool. Constant power laser and plasma cutters behave the same to the black box. In the advanced section, we need to add some code for the floating head. We need that G38 command to probe the torch in the Z direction to sense the height of the material. We will then want to move the torch up 1 millimeter to unload the floating head and then set the position to 0. Just a heads up, OpenBuilds is constantly updating and improving their software, and it's very likely in the future that you will just have to check a box or enter some settings about your floating head instead of having to type in this raw G code. Next, I'm going to import a DXF drawing of an engineered square, which is really just a glorified right angle. I will create a toolpath from this drawing, and for the operation, I will select plasma outside of path so that the part retains its dimensions. The Z-safe height and feed rate are fine for now. I will play around with the speed after this cut to show you the different effects of speed on plasma cutting. From that straight cut that I just finished, I can measure the kerf, or the size of the void that is left over from cutting. I measured about 2 millimeters. For the cut height, I want 5 millimeters. In advanced settings, it's important to make sure that IHS, which stands for Initial Height Sensing, is on. This will pin that code we wrote for the floating head to the G code at the start of a toolpath, which will allow the plasma cutter to get an accurate measure of the height of the material. We will generate some G code and export it to OpenBuilds control program. The G code is ready to go, but I made one small modification that I want to draw your attention to. During the straight line cut, it seemed like the x-axis started to move before the primary arc was fully established. What that means is that the plasma cutter didn't pierce the material before it started moving. So what I did with this code is I added a small delay with a G4 command so that the plasma cutter will pierce the material before the CNC frame starts moving it. Alright, it's time to click play. There was no part of that toolpath that was left uncut, so it was very easy to lift the square out of the stock material. There was a little bit of slag present, but I was able to knock that off with a flathead and a hammer. I checked some of the dimensions with my calipers. This specific dimension should be about 25 millimeters, and I was shocked to find that the plasma cutter was able to get this part within about 200 microns, which is crazy. I also checked the squareness of the square with the real square, and again, I'm just kind of blown away by these results. Really a testament for how capable the CNC table is. Obviously this is a great kit, but you also need to take your time in assembling it, and if you put some time into it, what you'll get out is some really accurate movements. Speaking of movement, I want to circle back and discuss feed rate and plasma cutting. The speed at which the plasma torch moves has a significant impact on the quality of the cut. The optimal speed is going to depend on a variety of factors. The two most important being the amperage at which you're cutting at and the thickness of the material. I'm cutting at 30 amps, and this stock material is 11 gauge mild steel, which is about 1/8 of an inch thick. Most plasma cutters have lookup tables that tell you what the optimal speed is for a certain thickness. However, let me show you how the presence of dross can indicate whether you're cutting too slow or too fast. Recall that the first square I cut out was at 1000 millimeters per second, and that speed had minimal dross. The second square that I will cut out will be at 200 millimeters per second, which is 1/5 the speed of that original cut. Notice this solid line of dross that resembles a weld bead. This is known as low-speed dross, and it forms because the torch is moving too quickly, and under these conditions the arc is not being fed enough material. Instead, the arc has to expand in order to keep its path to ground. This wide arc is outside of the high-pressure compressed air, so molten material doesn't get blown away. Low-speed dross is easy to knock away with a hand-scraping tool, but it can affect the part dimensionality because of the large kerf. The third square I will cut out will be at 2000 millimeters per second. On the bottom of the part, we see a thin line of dross that is often dotted in appearance. This dross is difficult to remove with hand tools and is known as high-speed dross. In this case, the torch was moved too quickly for its amperage setting, and the bottom of the arc lags behind the top of the arc. Again, the compressed air coming out of the nozzle is not effective at removing the dross in this situation. The fourth square that I will cut out will be at 3000 millimeters per second. This was so quick that there were sections of the toolpath that didn't fully pierce the metal. This is a dead giveaway that the torch is moving too quickly. I do want to point out that there are other causes of dross, such as worn consumables and low compressed air pressure. But typically, analyzing the dross is a good way to optimize your speeds. Before I cut anything else out, I want to talk about why I picked the Cutmaster 40. There are a lot of low-frequency plasma cutters on the market that will work great with a DIY CNC. The differences between some of these plasma cutters is subtle, so I compiled a list of compatible plasma cutters on my website, so check that out if you're in the market. However, as a guy that runs his shop out of his garage with a limited budget, my options were quickly narrowed down. Plasma cutters consume a lot of power and compressed air. The name of the plasma cutter usually indicates the maximum cutting amperage of the plasma cutter. Hypertherm's PowerMax 45, which is very popular for CNC, has a maximum 45 amps of cutting power. For this reason, Hypertherm recommends that you plug it into a 50 amp 220 volt outlet. My 220 volt outlet is 30 amps, but it is close to my breaker, so I could rewire that for 50 amp. But to be honest, I don't see myself cutting half-inch thick material, so I narrowed my search to 30 amp plasma cutters like the Hypertherm PowerMax 30 and the Viper Cut. But I was disappointed to see that these plasma cutters have a duty cycle of about 35%. If you're not familiar with duty cycle, this means in a 10-minute period, the plasma cutter can only cut for 3.5 minutes. The rest of the time, the cutter needs to cool down. This low duty cycle is not ideal for CNC. I revisited the idea of getting a higher amperage plasma cutter and running it at 30 amps. With the Cutmaster 40, you can get a duty cycle of 60% when you run it at 30 amps. Most plasma cutters that I looked at had significantly higher duty cycles when you run them below their max amperages. The other consideration when buying a plasma cutter that often is forgotten is the amount of air these little guys consume. Let's look at the PowerMax 45 again as an example. This plasma cutter needs 400 standard cubic feet per hour of air at 85 psi. The rule of thumb is to multiply the required airflow by 1.5 to 2 times to find an appropriate air compressor. This scale-up factor is needed to account for the fact that manufacturers measure the airflow of their compressors under the perfect conditions, and real-life performance will always be less. Also, the air will have to pass through filters to remove moisture and particulates, which will decrease airflow. So we would need an air compressor that supplies 600 to 800 cubic feet per hour at 85 psi. It's more common to see this number in cubic feet per minute, which would be 10 to 13.3 CFMs for our example. Air compressors that produce this much airflow cost more than $1,000 and require 220 volt power. My air compressor is a 110 volt, 4 horsepower California Air that produces 5.3 CFM at 90 psi. So I tried to select a plasma cutter that could run on this airflow. Online I saw that the Cutmaster 40 needed 2.8 CFM at 90 psi, so I thought that I was golden, but the manual contradicts the specification and says 5 CFM is required. I called Thermodynamics multiple times about this contradiction, but their plasma specialist never returned my call. However, watching the pressure gauge on my air compressor while the plasma cutter is cutting, it seems like it's more likely that this plasma cutter requires that higher CFM in the manual, which means my compressor is undersized. When you don't supply your plasma torch with enough air, then the aerodynamics of the torch are off. Engineers carefully design the components that go in the torch, like the swirl ring, to turn compressed air into a swirling vortex that confines the plasma to a column. If your flow rate is a little lower than what is expected, like mine is, the plasma cutter will still work, but the plasma will not be a uniform stream, which will affect cut quality. It is likely that I won't be able to get dross-free cuts. Just keep that in mind as I continue to churn out parts. My plan is to stick another 220 volt outlet in and to save up some money to buy an air compressor with more airflow for the future. I hope that provides you with some insight on why I purchased this Cutmaster 40, even if I was misled a little bit on the airflow rating. After only making a couple of cuts, I can see that plasma cutting is a lot of fun when you're not messing around with EMI. But it's important to keep in mind that there are stringent requirements for power and air. Next, I'm going to show you how to generate toolpaths in Fusion 360 for this plasma cutter, and then we're going to make some more stuff. This is going to be a very quick tutorial on how to generate plasma cutter toolpaths in G-code in Fusion 360. As I build more CNC machines, it'll be nice to do all my computer-aided manufacturing, or CAM, in one program. Fusion supports 3D printing, milling, turning, and cutting. Cutting includes not only plasma cutters, but also lasers and water jets. I put together a little design in Adobe Illustrator and exported it as a DXF file. I like to import the drawing onto the XY sketch plane because this will make it very easy to set up the work coordinate system in a later setup. I will extrude the sketch. The actual mount doesn't really matter, but to match real-world dimensions, I will extrude this design 1.5 millimeters because I will be cutting it out of 16 gauge mild steel. I will switch to the CAM workspace by clicking on Manufacture. First, we need to set up the operation, stock material, and work coordinates. The operation type will be cutting. I will put the origin of the work coordinate system at the bottom left of the stock material. Notice how the digital axes match the real-life axes of the plasma cutter. I like to make the stock material as small as possible, that way wherever I place the torch at the start will be the origin of the toolpaths. So the default stock side offset of 1 millimeter is fine. I do need to change the top offset to 0 because plasma cutting is a 2D operation, so a top offset doesn't really make sense. Now we can add a cutting operation. I will pick a plasma cutter as a tool. This default tool has a kerf size of 1 millimeter. My plasma cutter has a kerf of 2 millimeters. I will make this change after I finish configuring this cut. The feed rate is going to be quick because 16 gauge steel is thin. I have found 4,000 millimeters per second to be an appropriate speed. I will set the lead in and out to be the same speed as well. We will discuss what these settings are on a later tab. In geometry, we will select the model. Notice how the toolpaths become blue. You can choose to add tabs to your parts, which will hold everything to the stock material. Tabs can prevent parts from dropping into the water table or rising up and colliding with the plasma cutter. I'm not going to use any tabs for this cut, so I will move on to the heights tab. For plasma cutting, I have yet to change the clearance height or any of these other obstacle avoidance settings. I have found these defaults to work fine. Next, we will move on to the passes tab. These settings are very important. Counterintuitively, we don't want the tolerance to be too tight. Tighter tolerances, which are lower numbers in this field, will result in Fusion generating really short movements as it approximates curves. A lot of tiny movements actually slows down the machine through a phenomenon known as data starving. There is more information here on why this occurs, but as we discussed before, slow speeds can result in the plasma cutter consuming too much material, which can affect part dimensionality. For my plasma cutter, I have found a tolerance of 0.1 to balance speed and accuracy. I'm not going to get into what sideways compensation is, but by hovering over the field, you can learn more about it. What is important is that Gerbil, firmware that is running on the Blackbox, does not accept G-code compensation commands like G41 and G42, so if you use left or right compensation, you need to have Fusion generate the coordinates in the computer and not send compensation commands to the Blackbox. I'm going to use a center compensation because this is just an artistic design and I'm not worried about part dimensionality. I always turn on smoothing because it attempts to reduce the number of segments in a curve, which also prevents a lot of short movements. Finally, in the linking tab, we have lead in and lead out settings. These are important settings because they allow you to pierce the material at a sacrificial site away from the toolpath and then lead into the toolpath. When you pierce the material on a toolpath, the beginning part of that path will be wider because there's a waiting period where the plasma cutter dwells at that pierced location. While lead ins and lead outs are great, you don't want the distance to be too far because then Fusion will throw errors when you try and cut out smaller features because there won't be enough room for the requested lead in. I have generated the design before, so I know that with a lead in of 5mm, Fusion will not be able to cut out this bottom feature, so I will switch this to 3mm. Let's click OK. It will generate the toolpath, but we need to edit the curve size. Right-click, Edit Tool, change the curve size to 2mm, regenerate the toolpath. We can simulate the cut. Everything looks good. We have a warning here, but to be honest, I'm not sure what toolpath was discarded because the simulation looked fine. We will click on Post-Process to generate the G-code. I adapted an existing post-processor to work with the lead plasma, which you can download from my website. These dimensions are in inches. I will set the cut height to 0.15 inches, pierce delay to 1 second, and then I will turn the torch height control off. This is a feature I do plan to add to the plasma cutter in the future, but I will most likely have to switch controllers. Anyways, we will press post and then load the resulting file into OpenBuilds control and then cut it out. Before I cut out that part from Fusion 360, I have to tell you some bad news about the 3D printed torch holder. Off camera, I was having the plasma cutter take long cuts to learn more about its duty cycle and my supply of compressed air. Turns out that the retaining cap gets pretty hot and this heat softened the PLA holder, which caused the plasma torch to lean. PLA isn't known for its heat resistance, so it really wasn't the best choice for this application. At this point, I wanted to mill a torch holder out of aluminum, but I figured that my average viewer who may want to build the lead plasma is more likely to have a 3D printer than a mill, so I started to investigate heat-resistant filaments. Unfortunately, most of these filaments need to be printed on specialty printers that have a heated chamber and a high-temperature extruder. However, I found a filament from Protopasta that is a heat-treatable PLA known as HPLA. Parts printed from HPLA can be baked in an oven, which allows the polymer chains that make up the material to partially organize into tightly packed structures, which gives the material higher heat resistance. Protopasta claims that parts printed from HPLA have a heat resistance 3 times that of normal PLA after being heat treated. So far, this HPLA holder has not softened, even at longer cuts. Now, the thought of the plasma torch slipping out of its holder reminds me that I need to provide a disclaimer for this video. Plasma cutting is obviously dangerous, and you should not build one without fully understanding the hazards. I strongly recommend to never leave the plasma cutter alone when it's running. All the content presented here have been my efforts, and if you choose to follow in my footsteps, you're doing it at your own risk. With that out of the way, let's cut this Fusion 360 part. Before I end this video with a montage of a few plasma cutting projects that I've completed, I want to make a couple final remarks. First off, I'm very happy with how the mechanical and electrical systems for this CNC frame turned out. Yeah, I had some problems with EMI in the beginning, but throwing money at the problem by buying a low-frequency plasma cutter quickly fixed that. However, I'm still not quite satisfied with this solution, so I've been searching for something cheaper because the Cutmaster 40 almost doubled the price of this entire build. So I did a little bit more research and I stumbled upon a plasma cutter called the Cut 50L, which is less than $400 and is advertised as low frequency. Will it work with the lead plasma, or is this just another imported product that makes baseless claims? Answer that question in my next video. So get subscribed because you're not going to want to miss that or future projects that I have planned with this plasma cutter. Also follow me on Instagram for more day-to-day updates. I know that my video release schedule can be a little sporadic. If you want to build the lead plasma, then you're in luck because you can buy all the parts at the OpenBuilds online store. I've been told that OpenBuilds will eventually offer a kit allowing you to purchase everything you need with one click, but until that kit is available, you can follow the bill of materials posted on my website. Big thanks to OpenBuilds for supporting a small creator like me. Let's just say this video was less stressful to make without the monetary pressure that's been associated with my bigger projects. I'm looking at you, Mill. With that said, check out this montage of the plasma cutter in action. I'll see you guys soon.
I mean, the dog hair thing.
Well, I think you kind of have
get
to.
why you
Okay, yeah, you
shake
kind
it
of
a
have
little
to
bit,
stir it.
and that I don't get why you would freak out.
Not her hair.
Oh, that no.
No.
Hey, we can pull hair from your head and get out of that bitch.
You want to try pulling my hairs?
Yeah. We're not gonna give you any pain medication.
No.
Jail, no. Get away.
Yeah.
No.
Yeah.
Okay.
No butter for you.
Well, it looks like, you know, those little Jiffy popcorns. You guys
Yeah.
are too young for that.
I think I get
Jiffy,
the general
anybody
idea.
remember the Jiffy Pop? It was like a pan with a...
I never got that. It's the least.
Take the whole thing off and put it on the ground because you're going to try to flip it and then we're going to dump all the veggies in the coals. And that would be very sad.
Ooh.
That was good.
Yum.
Dang, those do look good.
They smell good.
Are they cooked?
They look cooked.
Oh, I think you seasoned them right.
Yeah, just some salt and pepper.